In this video, we're going to be looking for a power series representation of the arctangent. And where we're going to start is with a power series we know something about. That happens to be our power series for the function 1 over 1 minus x, which is the power series from n equals 0 to infinity x to the n. So the first thing we need to figure out is how we can relate arctangents to anything involving this type of rational function form of a 1 over 1 minus x or 1 plus x type stuff. So let's make some observations first. So the first thing we're actually going to do is just come ahead and take our function that we care about, the arctangent of x. And well, what I want to do is come across here and actually take the derivative of the arctangent. And the derivative of the arctangent is equal to the function 1 over 1 plus x squared. So the idea being here, we have this relationship now between some function that looks like 1 over a 1 plus or minus x type thing that we can sort of go back and relate to the power series we know something about for the function of 1 over 1 minus x. There's just going to be a couple steps to get us to tie that information in. So the first one was making this observation that the derivative of arctangent is 1 over 1 plus x squared. The next observation for us is going to feel very similar, but it's going to basically say, hey, how can we actually get a relationship for our function 1 over 1 plus x squared and arctangent directly? And well, just coming across with the relationship that we have from the previous line where we did the derivative, well, using the fundamental theorem of calculus, if we integrate both sides, what that'll basically give us is this right-hand side this is just whatever that integral is. But we know that integral through the fundamental theorem of calculus from the left-hand side is the arctangent. So basically putting these ideas together, if we have a power series representation of 1 over 1 plus x squared, we can go ahead and integrate that, and that'll give us a power series for the arctangent. So let's go ahead and do that next. The third thing we need to figure out is what that power series is, again, for 1 over 1 plus x squared, so we can integrate it to get us that arctangent on the left-hand side here. So we really are interested in the power series for 1 over 1 plus x squared. However, what we know at this point is the power series for 1 over 1 minus x, and that's equal to this power series on the right-hand side of basically x to the n. So this is the idea where we're going to use what we know and try to do a composition of functions, or basically try to create the stencil, like I've been calling it. So we start off with what we know. We have 1 over 1 minus x, and that's equal to the power series from n equals 0 to infinity of x to the n. The idea being anywhere there's an x on both sides of this relationship, I'm just going to go in and basically draw parentheses around it. And once I have those parentheses there, I'm going to go ahead and get rid of the x inside. The idea being, whatever I put in the parentheses on this left-hand side, I'm just going to go ahead and put in the parentheses on the right-hand side here to maintain that relationship. So we're going to use this idea of this stencil or composition of functions. And what we need to do, though, is try to morph the function we care about, 1 over 1 plus x squared, to fit into this type of form, where we have basically a 1 over 1 minus something. So let's go ahead and start off with the function we know something, or start off with the function we care about. So I'm just going to move this stuff over to the left-hand side here. So we can do a little bit of algebra here. We can get this into the form of 1 over 1 plus x squared is the same thing as 1 over 1 minus a minus x squared. And now if you look at that form, this form is exactly what we need for this form on the left. It's just that inside of our parentheses, we are going to have a minus x squared. So what this says is we can now write this as the power series from n equals 0 to infinity of the quantity, again, going inside our parentheses, just like on the left-hand side, raising that to the n. We're going to put in those parentheses the minus x squared inside. And then just doing a little bit of algebra here, because we want to try and isolate the x terms by themselves. Since inside of the parentheses, we have the product of things being raised to the same power, we can split this into the individual factors raised to those powers and then multiplied together. So we can write this as a minus 1 raised to the n times our x squared raised to the n, which, since now we have this x squared raised to the n, we could multiply those powers together. So this gives us the series from n equals 0 to infinity, minus 1 to the n times x to the 2n. And that's equal to the function 1 over 1 plus x squared. So now that we have this relationship, what we saw before was, well, if we take this function and we integrate it, it gives us back what arctangent is. So we're basically going to take what we saw before, that arctangent's equal to the integral of 1 over 1 plus x squared. So let's go ahead and fill that in. So this will be kind of observation 4 for us. If we have that, arctangent is equal to the integral of 1 over 1 plus x squared dx. The next move we're going to make is basically substitute what we know for 1 over 1 plus x squared in terms of its power series. So substituting that power series into the integrand, we have the integral of the series from n equals 0 to infinity, a minus 1 to the n times x to the 2n. And that'll still be equal to, on the left-hand side, that arctangent. So now what we need to do is integrate that power series. And again, when we're integrating a power series, we are integrating here with respect to x. So the only thing the integral really does care about are the terms that have x's attached to it, just really that x to the 2n. So we can think about this equaling the following. Left-hand side's the same, but that integral sign can basically pass any term on the right-hand side besides the ones that have the x's attached. So we still need the integral of x to the 2n with respect to x. And now what we see is we're taking the integral of really just a variable raised to a power, so we're going to be able to use the antiderivative power rule. So left-hand side, we'll still have this as the arctangent. On the right-hand side, we have the series n equals 0 to infinity, a minus 1 to the n. And now if we do the antiderivative power rule, we'll take that power of 2n and we'll increase it by 1. So we have x to the 2n plus 1. And we'll take that 2n and add 1 to it and divide by it. So we have divided by 2n plus 1. And then, of course, since we did an integral, we have a plus c. So the last step that we can do is try to figure out what that integration constant actually needs to be. And for us, we can try evaluating both sides at x equals 0. So we'll have the arctangent evaluated at 0, and inside of that power series representation, we'll also evaluate it at 0. And again, what we're looking for is the value of that integration constant. So having evaluated both sides at 0, well, that power series is just going to all equal 0 since we're multiplying every single term by a 0 there. And the left-hand side, the inverse tan or arctangent of 0, well, that thing's also 0. So what we have is 0 is equal to the 0 plus c, or in other words, we find that that integration constant is actually 0. So what we actually have as power series of the arctangent here is basically what we found a couple moments ago, just with no additional integration constant. So the power series representation of arctangent can be seen as that following power series, the series from n equals 0 to infinity minus 1 to the n times x to the 2n all over 2n plus 1. And this power series actually gives us a pretty powerful tool because we're actually going to be able to find some values of pi that can be expressed in terms of an infinite series. So for example, if we evaluate both sides at x equals 1 here, we can take this relationship where we have the inverse tan of 1 equaling that power series evaluated at 1 as well. And what we know is, well, the inverse tan of 1, that gives us a pi over 4. On the right-hand side, we have this is from n equals 0 to infinity, minus 1 to the n. And when we have a 1 to any power, that just gives us a 1. So all we have on the right-hand side is a minus 1 to the n all over a 2n plus 1. And if we just multiply both sides by 4, we have a series representation of the number pi. So we can actually find what pi is equal to if we want to express pi, the number, in terms of an infinite series.